Hi, everyone, and welcome to the low-rank adaptation of large language model lecture. The lecture is going to take about 30 minutes. That's how we planned it. We are going to talk about what is the low-rank adaptation of large language model, and we're going to talk about a little bit of the math behind it. And then I think the most important thing of this lecture, of theme of this lecture, is that we will be able to dive in to an actual code and implementation of the low rank adaptation for a toy problem in Python, but it is still going to show you how this scheme works and how to use it. Karan, I'm sharing my screen, right?
Yeah.
Great. Can you let in all the people that are joining?
Yeah, I'll take care of that.
Okay, because I can't see because I'm sharing my screen, I can see only my screen here.
Okay.
All right. So I'm going to start. I'm going to start with the presentation and some math behind this concept. My name is Nir Regev, and I'm one of the founders of Aleph Zero. Aleph Zero, Aleph0.ai is an AI consulting company. We do a lot of AI type projects on sensors like radars, lidars, cameras, and on other stuff as well. You can check our website if you want. It's aleph0.ai. Mr. Karan Jakar is one of our principal AI scientists, and he's actually going to present the part in which we run through the code and implementation and training, and he will do the second part of this presentation. All right, so let's get started. Okay, so this is the topic for this lecture is the LoRA, the low rank adaptation of large language models. This is work that was introduced to the community in October 2021 by Hu et al. From Microsoft. It's a Microsoft work, and excuse me, and the main applications for this work was a large language model, but the context that they presented it is large language models. But as you will see in the presentation today, as well as the actual demo, that it can be taken into any deep learning model. It doesn't have to be a language model. Now, since then, a lot of work has been done around LoRA, and a lot of variants were developed. And we are now, this lecture is presenting the legacy LoRA implementation. But just know that if you want to do further research, or you want us to do further presentation on other topics, you can ask for us. You can ask that from us, and other I would say variants of LoRA were AdaLoRa and LoRa Plus and Vera, which is vector based, and we have more. We have more in the industry right now. LoRa is a seminal work in this field, and a lot of work is built upon it. Okay, so what is the LoRa's idea? Okay, so first let's write down the common. We all know the common deep learning linear model. This is y equals w, and let's call it w naught, x plus b, where w naught is the weights matrix. These are the parameters that we usually train for in a deep learning scheme. All right, these we call it weights, and the amount of these is the amount of parameters that the model is trained on using gradient descent. And b is of course the bias of the model. Okay, now the idea behind LoRa is to get a new weight matrix, let's call it W, which is comprised out of this original matrix W naught, which is already pre-trained. Let's write it down. This is pre-trained. Okay, and freeze it and train or change only this matrix, B times A. And this is the idea behind LoRa. Add a matrix that is, we call it B times A. It's the same dimension as W naught. And train only this B times A matrix. And we will see why it is so beneficial. Let's dive into the dimension of the matrix B. We see that the matrix B times A is comprised, this matrix here is comprised out of the multiplication of two submatrices. The dimension of B is, let's write it down in the paper, it's the same notation, it's D times R. And let's say that R is 1 for the purpose of this demonstration. So that makes B a column vector of size D, right? D rows and 1 column. D times 1, sorry. D times 1. Okay, the dimensions of A, so this is a column, B is a column vector. A, to satisfy the requirements that B times A will be a matrix, the same size as the W naught, we have A as a row vector. So let's write the dimension of A. A is R times K, and say, like before, that R is 1. And that yields a row vector of size 1 over K. Okay? The dimension of B times A is obviously D over K, which is the same dimension as W naught. Okay, so in essence, we are constructing, by construction, we are constructing a matrix that is the same size as W naught and adding it to W naught. Okay, now the trick of LoRa is the rank. What is the rank of B times A? If we take a column vector multiplied by a row vector, the rank will be 1. Okay, but this is for R equals 1. In general, the rank of B times A will be R. And that's the that's the secret of LoRa. It's a low rank adaptation for a language model or for any deep learning model. Now what is the extra number of parameters? The extra number of parameters is D plus K when R is 1. When R equals 1. In general, it will be R times D plus K. Now, note that this is, and in the paper they present like the dimension of D plus K is maybe 2 orders of magnitude less than the number of weights we have in W naught. So we are training very little addition to this whole network. Let's talk about the way that they initialize the LoRa matrices. So the initialization is as follows. B is initialized by zeros. When I say 0, I mean a matrix of zeros in the dimension of B, in the size of B. And A is randomly initialized with Gaussian zero mean unity variance. In other words, it's rand n in MATLAB, and then NumPy it's rand n of the size of A. Okay, the back propagation, and this is important, the back propagation and the gradients that we update are done only with respect to BNA. So W naught is freeze, we freeze it, and we backprop only on BNA. We do the forward path, and we backprop again only with respect to BNA. That's the secret of LoRA. That's what makes it so lucrative, so to speak. Okay, what's the advantages? So it doesn't really add another latency inference. When deployed in production, we can explicitly compute and store W equals W naught plus BA and perform inference as usual. Another advantage, which is a big advantage, is that we can calculate BNA for one downstream task, okay? And then we can train another BNA, let's call it BA sub 1, to do a different downstream task, and we can switch between them in inference very easily. How do we do that? We calculate W naught from W old, let's call it W sub old, plus minus, and then we are subtracting B times A old, okay? And we are constructing a new weight matrix, let's call it W sub nu, as W naught, the original W naught that is always frozen, and we add to it the new downstream task BNA. And it lets us do that very efficiently and with a lot less memory and storage comparing to retraining W naught for each and every downstream task that we do. Okay, now I want us to go and dive into the Python code that Karan prepared for us. But first, let's have a round of questions if you guys want to ask anything.
Nothing on the chat. Maybe we can switch on the mic.
Okay, 1 second. Let me see. Okay,
I
great.
allowed it.
Great. Yeah, good. Good. Okay, so I'm turning it to you, Karan, and take it away.
Okay. Hello, everyone. Let's going to go through the code, which will show that how helpful is LoRA. Let me share my screen first. Okay. Let me know when my screen is.
I can see a screen, Karan. You can go ahead.
Yeah. So for the demonstration, we are going to train a small classification network, neural network for classification on MNIST dataset. It's a dataset for digits like from 0 to 9. And the image size is 28 by 28. And we need to classify basically what digit is in there, that image. So here we do basic import. We are using PyTorch library for training our network, and Torch Vision for importing the data set and applying the transformation, like converting it to tensor and normalizing it. Here we loaded our MNIST data set. So MNIST data set comes with Torch Vision. So basically we download that. We created a train loader. Basically we want to load batch by batch, size of like 10 images at a time. And then we also create our test data set also. So what we are going to do, first we are going to train the classification network simply on training dataset. Then we will add LoRa weights to that network. This is our network, classification network. And we are going to train that network with added LoRa weights on only a single digit, for which we want to improve this. And later on, we will compare that how a simple network performs for that single digit and how after adding just LoRa weights performs. And we will see the size of both networks also, simple one and the network which has LoRa weights. So this here we define our classification network. And for the experiment, we kept the hidden sizes like network size to be very large, 2000 and 4000, so that we can compare like adding LoRa weights is the LoRa weights are very small compared to training the whole network. The network is quite simple. We take input as an image like 28 by 28. We flat it, basically reshape it and convert it to a single dimension. And then we pass it to our first linear layer, applied LU, second linear layer and applied LU, and then linear layer, third linear layer. We return this. So an output size would be like 10 array of size 10 because we have 0 to 9, like 10 classes. So probability for each class. And here we have our training code. So for each epoch, what you want, we set the network to training mode. And then we load one batch. Batch has 10 images. And we pass those images to our network. Basically, two devices for shifting the images, the images and labels to the GPU. We pass it to our network. Then we compute the loss. Use the loss function, compute the loss. And then we find the gradients, back propagate, and then we use the optimizer to update the weight based on the gradients. Let's train it for, let's say, 1,000 iteration, like one epoch. This should be okay. We need just run these cells also. We are keeping, like, we're training at a small network and just for this demonstration. So it will be very fast, but the same concept can be used like on any large model. Let's just make a copy of our original weights so that later on we will check that after train, because when we train LoRa model with LoRa weights, we basically freeze the original weights. We don't change the value of those weights. So here we are just keeping a copy of our original weights. So later on we can compare that nothing was changed after training model with LoRa weights. Now this function is for test data set. So we kept a separate data for loaded, separate data for test also. And it will list out the wrong counts for each digit. So if you see here for digit 9, we are getting very high wrong. So what we want to do, we are going to train the same network, but we are not going to train the original weights. We're going to freeze them, add LoRa weights to it, and then train the network just for digit 9. So that new network will perform much better for digit 9. And it will be very fast to train and very small network. Very small parameters, yeah. So right now, if you see the total parameter in our network is around like 9.6 million. And now let's see how we can add. So in Python, what we can do, there's a concept of like parameterization. Using that, we basically add LoRa weights to any like layer. So linear layer will have like a matrix called like weights. So it will have, so a linear layer will have a parameter weights, which will have a metric. So basically what you're doing, we're going to add a LoRa layer to that LoRa parameterization basically. So let's just add that. And then we will check the network size again. This is just printing out like after parameterization, how our network looks. For each linear layer, we have a parameterized layer in between, which will have like a LoRa parameterization here. And now let's check again the size of original weight and also LoRa. So if you check, the original parameters were around 9.6 million. Then after adding LoRa, we only increased like 12,994 parameters only. That's around 0.13% of the total weight. So now when we are going to fine tune or like train it for just for 9, then we only need to train like 12,794 parameters. That's like just training 0.13%, not the whole network. We don't need to train whole. And let's just, let's now freeze the network like the original bits. So what we are here doing is that any layer which doesn't have name LoRa in it, we want to set that gradient to false so that no gradient is computed when we perform the back propagation for those layers. And now we're going to train it just for 9. So if we look at here, we load the MNIST data set again, then we created like a exclude indices. We say, but if where the target is not equal to 9, just put them in the exclude indices, and then we will just like remove those. So we are just keeping the data related to 9, like images and the label, just for the 9. Again, correcting train LoRa, pass as keeping track. Now we're going to again train the network. This network is going to only train the LoRa parameters, not the whole network. And we're just going to train it only for 20 iteration. That's also like will perform good, improve this. Now what we do, let's check that our original weights, which we kept in the starting, we kept saved it. And right now the network after the LoRa training, both are same. There should be no change in those weights. So for assert, we check assert basically checks whether this condition is true or false. So basically we are checking they are equal or not. And then let's just create another, this function will help us while testing, like whenever we want to enable LoRa parameters or when we want to disable basically. And now let's just, these are just for, we're just checking after like enabling LoRa weights, whether they are equal or not, just a few conditions we check. But the main interesting part we need to check is that how is the performance with LoRa enabled, basically like using LoRa plus the original weights. So if you see with original weight and LoRa, we get better result for design. Let's check without LoRa weights, only original weights. It will be same in this, equal to in what we had in the starting basic. So for digit 9, we see there's like 227 wrong just using our original model. But once we've trained it like with the LoRa weights, and we just trained it for 20 iterations just on the data set of digit 9. So now we have a model, and in not whole model, just LoRa weights like that 12,000 parameter, which performs really good for one specific task. That is predicting digit 9. So like this, we could train like multiple LoRa's for a different task. This is just an example. Like for example, we could have 10 LoRa's, one performing good for 0, one for 1, 2, 3, like that. So same can be applied to like other tasks like in LLM or in stable diffusion. We could have LoRa weights trained specifically performing good for one task. And because LoRa weights are very small compared to the whole network, and their storage is easy, so in deployment also they will have. But yeah, overall, we can see that it improves the results specifically.
Yeah, in this case, Karan, in this case, it was the amount of weights was 3 orders of magnitude less than the total amount of weights. Right?
It was
0.1%, you said.
Yeah, 0.13. Yeah.
Yeah.
0.1, yeah.
Yeah. Yeah. So 3
Yeah,
orders
it's
of
pretty
magnitude.
low.
Yeah, it's great. It's great.
Yeah, pretty
All
low.
right. Yeah. And any more stuff to show, Karan, or that's it for your part?
Yeah, that's it. Any
Okay.
questions?
Yes. Let's wait for questions. Meanwhile, I just want to say that the presentation as well as this code will be shared with you. Also, the video of this lecture will be shared. You will get an email from our webinar system that is sharing all this with you. And any questions you got after you take your time and refer to this material, you can always email me or Karan. Our email is our name at aleph0.ai. Okay, I don't see any questions, Karan, so I guess it was pretty much understandable and well taken. And guys, thank you for joining our lecture on large language models and low rank adaptations. We wish you a nice weekend and follow us online for more lectures in the future.
Yeah. Thank you, everyone.
Bye bye.
Thank you.
You. Thank you.